Hello, in this segment, I will prove this very important theorem we need for the following segments. F of t be a d-degree polynomial in ZP. ZP means all the elements from 0 through p minus 1, where p is a prime. We claim that any polynomial of d degree will have at most d roots. We will prove by induction. Okay, consider the case that d degree is 1, just d is a 1 degree polynomial. Okay, what is a 1 degree polynomial? A 1 degree polynomial means f of t will be a times t plus b, that's 1 degree, right? Because t power is 1. Okay, we have to assume a is not equal to 0, otherwise it's a constant polynomial. We are talking about a non-constant polynomial. This is implicitly assumed here. Okay, let's assume f of t is equal to 0. In that case, t will be minus b times a inverse. Okay, this will be the root. How many roots did we find? At most one root. If a is not equal to 0, we can convince ourselves that a times d plus b equal to 0 will help us to find the t. We know how to find a inverse. A inverse exists for all non-zero a's. That's the reason I say this is a root. So we proved that for a linear polynomial, we have a root. So the theorem is true for the base case. Well, let's assume now that f of t has at most t roots. And now prove the scenario that if you have a d plus 1 degree polynomial, it will also have at most d plus 1 roots. That's basically the induction principle. So we are going to assume f of t has at most t roots, and to prove that in the case that f of t is a d plus 1 degree polynomial, it has at most d plus 1 roots. So consider d plus 1 degree polynomial. Is nothing but c d plus 1. C is a coefficient, constant, times d power d plus 1, cd into d power d, and also on until c0. Now we consider this polynomial f of d. There are two possibilities, right? There are no roots or there are roots. If there are no roots, that means there are 0 roots. And we can clearly see we are done because 0 is less than or equal to d plus 1. At most d plus 1 roots. We are done. Consider now the scenario that f of d has some roots. Okay, let's assume f of d has one root. Let's call that root to be r. In the previous lemma, we proved that f of d can be rewritten as t minus r times g of d, because r is a root. Therefore, t minus r must be a factor of f of d. Okay, this is proved in the previous lemma. Okay, but what can you say about the degree of g of t? G of t cannot be more than d degree, because f of t has a degree d plus 1, and we have a t here. That means g of t must be degree d. Okay, but what about g of t? We already solved the induction for d degree polynomial. G of t have at most d roots. Okay, therefore what can we conclude now? So this box can have at most d roots, because this is a d degree polynomial, and we also have t minus r in the front, and we assume r is another root. Therefore f of t overall has at most d plus 1 roots. Where did I use the fact that p is prime? Okay, let me now explain to you. Only in ZP, whenever you have x times y equal to 0, we can conclude x is 0 or y is 0. This is only true for ZP. Consider now the scenario that p is not a prime. For example, Z15. 15 is not a prime. It's made of numbers from 0 through 14. Consider this polynomial, x square minus 1. And if you want to find the roots of this polynomial, you can see here there are 4 roots. If you put x equal to 1, it will satisfy. X is equal to 4 will also satisfy, because 4 square is 16. 16 minus 1 is 15. 15 mod 15 is 0. Okay, everything is in mod 15 in this case, right? And 11 square is 121. 121 is same as 1 in mod 15, so you get a 0 there. And 14 square is 196. 196 minus 1 is 195, which is also 0 in mod 15. So we get 4 roots, even though the degree of the polynomial is only 2. So just want to be aware that this theorem is not true if the number p is not a prime number.